There was a problem, however. The reaction was reversible, meaning the ammonia would eventually start to decompose, reforming nitrogen and hydrogen. The rates at which ammonia decomposes and nitrogen and hydrogen react will soon be equal, and at that point the reaction would have reached chemical equilibrium. The chemical equilibrium for this reaction at 400 degrees Celsius is 1.64 times 10 to the power of negative 4. The equation for this equilibrium constant is also this. A reaction reaching chemical equilibrium is bad for industrial processes because less products would be made. Haber evaded this problem knowing Le Chatelier's principles, which states that a change to a chemical system at equilibrium would cause the system to shift in the direction that will reduce that change until it establishes a new equilibrium. One shift to the equilibrium would be a change in temperature. Since this reaction is exothermic, a lower temperature would shift the reaction to make more ammonia. However, the catalyst required at least 400 degrees Celsius to be efficient, so that wasn't an option. Industry standards requires between 400 and 450 degrees Celsius. Thus, pressure had to be increased. Because the reaction produces less moles than the reaction consumed, an increase in pressure would increase ammonia yield. Standard industrial pressures are between 200 and 400 atmospheres. Aside from that, ammonia also has to be constantly removed from the system to keep the reaction going, while nitrogen and hydrogen have to be continuously added in. In practice, gaseous ammonia is not removed from the reactor itself, since the temperature is too high. The hot gases are cooled enough for the ammonia to condense and be removed as liquid. Unreacted hydrogen and nitrogen gases are then returned to the reaction vessel to undergo further reaction.